April 10th, 2019. An image was released, and it quietly changed history. For the first time, humanity didn't see a simulation or a computer model. We saw the real shadow of a black hole. A bright ring of light wrapped around complete darkness. Exactly what Einstein predicted, but never thought he'd live to see. To capture this, 8 radio telescopes scattered across the entire planet worked as one. From the South Pole to Spain, Chile to Hawaii. Together, they turned Earth into one giant eye. The target? M87. Why this black hole? First, it sits at the heart of galaxy M87, 55 million light-years away. Far enough to study, close enough to see. Second, it's so massive that its event horizon is actually visible in our sky. If you swapped it with our sun, its edge would stretch all the way out to Neptune. Third, the angle. We're looking almost straight down at its disk, not edge-on. But here's what really sets M87 apart. What scientists discovered in recent years. Something that pushes physics right to its breaking point. Before we understand just how fast this monster spins, we need to rewind, back to where it all began. Picture a giant star, 20 times bigger than our sun, burning bright for millions of years. But now, its fuel is gone. When a star can't hold itself up anymore, gravity wins. The core starts collapsing. And this is where a supernova happens, sometimes shining brighter than an entire galaxy. But inside, something else begins to form. A singularity. It's not a point, it's not even a place. It's somewhere our physics breaks down completely, where density and the warping of space-time spiral toward infinity, where every equation we have goes silent. And around it, a boundary forms, the event horizon. Cross that line, and there's no coming back. Not for you, not for light, not even for information. From the outside, time itself freezes right at that edge. But for anything falling in, it all happens in an instant. A silent, endless plunge. This is how a black hole is born. But black holes don't just sit there pulling things in. They spin. When a star collapses, something called angular momentum gets conserved. The star's rotation doesn't disappear, it just gets compressed. Now imagine a massive star compressed down to the size of a point. Its rotation becomes almost impossible to comprehend. And this is where things get interesting. When a black hole spins, it drags the space and time around it along for the ride, a phenomenon known as frame dragging. Space itself comes alive, it moves, and you can't remain still, even if you try. Near the event horizon, a region forms called the ergosphere. In this region, even light can't stay motionless. It has to rotate. It has to move with the black hole. Step into the ergosphere and you'd feel it. An invisible current pulling you along. You're not just in space anymore. You're caught inside space that's flowing like a river. And this is the engine behind one of the most powerful forces in the universe. Because spin is energy, and that energy can be tapped. Channeled into jets of plasma, used to sculpt entire galaxies. And M87 is likely rotating at around 94% of the maximum allowed speed, making it one of the fastest spinning black holes ever observed. Surrounding M87 is a massive swirling disk, gas, dust, the shredded remains of stars. This is the accretion disk. The closer matter gets to the black hole, the faster it spins. And faster means hotter. First, thousands of degrees, then millions. So hot it starts glowing in X-rays, blasting out radio waves. But not everything falls in. Part of that material, driven by intense magnetic fields and the black hole's insane rotation, gets launched out through the poles. These are plasma jets. The jet of galaxy M87 extends for thousands of light years, moving at speeds close to that of light. Seen up close, it would resemble a luminous blade of plasma emerging from the heart of darkness. The power of this jet is on the order of 10 to the 37th power watts, energy comparable to the combined output of billions of suns, focused into two narrow streams of plasma. So where does that energy come from? The black hole is extracting its own rotational energy and throwing it outward. It does slow down, but that slowdown takes billions of years. A cosmic engine that never gets tired. Just 6%. 6% shy of the absolute limit. If it spun any faster, physics would start tearing apart. At this speed, the ergosphere is enormous, filling nearly half the space out to the event horizon. Space itself has become a massive whirlpool. This is what we saw in 2019. A glowing ring, 42 microarcseconds across, smaller than a coin held at arm's length, but more real than anything we'd ever captured. Follow-up observations showed something incredible. M87's jet is alive. Every 11 years it changes, brightens, dims, shifts shape. Probably because the amount of matter feeding the black hole fluctuates. Or maybe the magnetic field around it pulses and cycles. But one thing stays constant. This thing never stops. M87 isn't the only black hole we've photographed. In 2022, we imaged Sagittarius A, the black hole at the center of our own galaxy. But the differences? Striking. Sagittarius A, 4 million times the Sun, 1,600 times lighter. M87, 6.5 billion solar masses. M87 is way dimmer. Why? Because the gas around it is thin, just 1 atom per cubic centimeter. In conditions like that, the energy gets trapped in the matter itself. It heats up inside, but barely any light escapes. Those powerful jets, they pump heat into the gas between stars. So much heat the gas can't cool down, can't collapse, can't form new stars. Scientists call this active galactic nucleus feedback. Without M87, galaxy M87 might be packed with billions more stars than it has now. Black holes don't just destroy, they build, they balance. The next generation Event Horizon Telescope, the NGEHT, is already being built, and by 2030, it's set to change everything. It will sharpen our images by a factor of 5, and even capture short movies of gas swirling around M87 and Sagittarius A. It will measure spin with unprecedented precision, map the structure of the accretion disk, and maybe even reveal hints of quantum gravity. We're getting closer to watching black holes in motion for the very first time, seeing gravity operate at its absolute extreme, staring right at the boundary of what's real. A couple of centuries ago, we thought Earth was the center of everything. Then we realized even our sun is just one star among billions. Now, we're watching space and time themselves bend and flow. With its dizzying spin and violent jets, M87 proves something profound. The real universe is stranger and more powerful than anything we dreamed. And this is just the beginning. A journey taking us to the heart of the cosmos, to the edge of time, to mysteries we haven't even begun to uncover.